For centuries, Mars has captured human imagination. Its reddish glow in the night sky earned it the name the Red Planet, and for a long time, people wondered whether it might host canals, vegetation, or even intelligent life. Today, we know Mars is cold, dry, and largely barren. Yet despite its hostile surface conditions, it remains the most realistic candidate for humanity's first permanent settlement beyond Earth. The idea of living on Mars has moved from science fiction to engineering discussion. Space agencies and private companies have designed habitats, launch systems, and long-term mission plans. But the critical question remains: could humans truly live there permanently? Mars is not another Earth. Its atmosphere is thin, about 1% the pressure of Earth's. It is composed mostly of carbon dioxide. Temperatures regularly fall below minus 60 degrees Celsius. Liquid water cannot remain stable on the surface for long. Radiation from space reaches the ground with far less protection than on Earth, because Mars lacks both a thick atmosphere and a global magnetic field. The first challenge is simply survival. Humans cannot breathe Martian air. Any permanent settlement would require sealed habitats with controlled pressure, oxygen production, and carbon dioxide removal. Water would need to be extracted from underground ice deposits or recycled continuously. Food would need to be grown locally, since transporting supplies from Earth indefinitely is unrealistic. Radiation poses one of the most serious long-term risks. On Earth, our magnetic field deflects much of the harmful solar and cosmic radiation. Mars does not have that protection. Astronauts living on the surface would face significantly higher exposure, increasing the risk of cancer and other health problems. Any permanent settlement would likely need to be built underground or shielded by thick layers of regolith to reduce radiation exposure. Gravity is another unknown factor. Mars is only about 38% of Earth's gravity. We know that prolonged exposure to microgravity causes bone loss and muscle deterioration, but we do not yet know how the human body would respond to partial gravity over years or decades. Children born on Mars might develop differently. Long-term health effects remain uncertain. Then there is the psychological challenge. Mars is isolated. Communication delays between Earth and Mars can range from several minutes to over 20 minutes one way. Real-time conversation is impossible. In an emergency, immediate rescue from Earth would not be an option. A permanent Martian settlement would need to be self-sufficient and capable of solving its own crises. Despite these challenges, Mars also offers advantages. It has a 24.6-hour day, remarkably similar to Earth's rotation period. It contains water ice. Its soil contains essential elements that could support agriculture if properly processed. And unlike the Moon, Mars has a substantial atmosphere that provides at least some shielding and could potentially be modified over extremely long timescales. The concept of terraforming, altering Mars' atmosphere to make it more Earth-like, has been proposed. In theory, releasing greenhouse gases could warm the planet and thicken the atmosphere. However, current scientific assessments suggest that Mars does not contain enough accessible carbon dioxide to create a dense, warm atmosphere with present technology. Terraforming would likely require centuries or millennia, if it is possible at all. Therefore, any realistic permanent human presence on Mars will rely not on changing the planet, but on adapting to it. A permanent Martian colony would need to function as a closed ecological system. Air, water, and nutrients would have to be recycled with extreme efficiency. Waste could not simply be discarded. It would need to be converted back into usable resources. Advances in life support systems on the International Space Station provide a starting point, but scaling those systems for hundreds or thousands of people presents new engineering challenges. Energy production would be critical. Solar panels could generate power, but Mars receives less sunlight than Earth. Dust storms, some lasting for weeks, can significantly reduce solar output. Nuclear reactors may provide a more stable long-term energy solution. Reliable power would sustain life support systems, agriculture, and industrial processes. Food production would likely rely on hydroponics or aeroponics inside controlled environments. Martian soil contains perchlorates, chemicals that are toxic to humans, so crops would need to be grown in treated soil or artificial substrates. Water recycling systems would need to approach near total efficiency. Transportation between Earth and Mars presents another challenge. Launch windows occur roughly every 26 months. A permanent colony would need to minimize reliance on Earth resupply missions. Manufacturing capabilities, including 3D printing and resource extraction from Martian materials, would be essential. There is also the social dimension. A Martian settlement would develop its own culture, laws, and governance structures. Questions about property rights, citizenship, and autonomy would inevitably arise. Over generations, Mars could become not merely an outpost, but a separate branch of human civilization. However, permanent habitation may come with irreversible biological consequences. Humans born and raised in lower gravity might struggle to adapt to Earth's stronger gravitational field. Mars and Earth populations could eventually diverge physically over long timescales. Some scientists argue that becoming a multiplanetary species increases humanity's long-term survival probability. A catastrophic asteroid impact, global pandemic, or environmental collapse on Earth would not necessarily wipe out all human life if a self-sustaining colony existed elsewhere. But survival alone does not equal thriving. A Martian civilization would face constant environmental hazards, limited resources, and permanent isolation from Earth's natural ecosystems. The question is not simply whether we can survive on Mars. It is whether we can build a society there that is psychologically stable, economically viable, and biologically sustainable across generations. Mars is both inviting and unforgiving. It is close enough to reach, yet distant enough to isolate. It has water, yet no breathable air. It has a day like ours, yet a gravity unlike anything humans have ever adapted to long term. Permanent life on Mars is not impossible, but it is not simple. It would require technological mastery, social cohesion, and a willingness to accept that life on another world will never be the same as life on Earth. In the end, Mars may not become a second Earth. It may become something entirely new, a human frontier shaped not by oceans and forests, but by domes, tunnels, and red dust. Whether that future becomes reality depends not only on engineering, but on the choices we make in the decades ahead.